Great. So welcome back, everyone, to day 2 of the meeting on frontier models of event horizon scale accretion. So in this morning session, we'll have talks about IR studies of the Galactic Center and GR tests around M87 with the Event Horizon Telescope. It's a very exciting week for IR studies of the Galactic Center with the awarding of the Nobel Prize in Physics. And so, of course, congratulations to the laureates, but also to the large research groups involved in all that work. And so we're very lucky this morning that Tuan is our first speaker, who's been a key member of the UCLA team doing these studies for many years and is now just started as a faculty member at UCLA. So Tuan, please take it away. And today I'll tell us about Sagittarius A related work, I think mostly, which he's also been a big part of. So Tuan, please take it away.
Right. Thanks a lot. It has been a really exciting week, and I'm really excited that Andrea and Reinhardt got the recognition they deserve for doing all this work, and I think it also speaks to how interesting the Galactic Center is. And so today I'm going to talk about Sagittarius A in the near infrared. Let me share my screen. So Sagittarius A has been observed in the near infrared for a really long time. So I'll just go through a bit of a brief discussion of that, and then also what happened in 2019, where it became the source became much brighter than we'd had ever seen it. To begin, I just sort of want to reorient ourselves in the Galactic Center. Many people have already know where the Galactic Center maybe is, but I always like to think about you know, how the scale that you need to observe, right? So this is the sky in optical light, and then as we zoom in, you'll see that in the near infrared now you can see many more stars. And this image is taken with Spitfire, and then as you zoom in, this is now with Hubble Space Telescope. As you can see, as you get to the very center of a galaxy, even Hubble doesn't have the angular resolution to resolve the sources there. And eventually, if you zoom in all the way to the center, you can use adaptive optics to measure the orbits of the black hole. Now, many of you have probably seen this picture. It's very cool. It shows that there's a black hole exists. But I also really like to show the actual data that we take in the near infrared. And so this is going to be an animation, or basically a series of frames, literally the raw data, not really raw, it's the process data, but just roughly aligned, so you can see the data quality over time. And so we start at 1995, and then it goes all the way to 2018 in this video. So since it goes really fast, you can see now we've now circled SO2, and as SO2 goes around, you'll notice that there's a spot here that turns on and off. If you look carefully, let's see this. So in hindsight, we should have detected it in 1995 in near infrared, actually, because now we know very precisely where Sagittarius A is. You just need to go look at that spot, right? But that wasn't. It took a while because for a long time it wasn't even clear, you know, where the center was in this image until you got enough orbital coverage of the stars to know exactly where to look. And you'll also notice that in this series of frames that the image quality changed a lot. So in early days, in the you can see that it was with speckle imaging, and so you didn't see very many stars. And then in about 2005, adaptive optics turned on, and you can see many more faint things in the background as well. And that has totally helped our studies of Sagittarius A in the near infrared. So my talk today is mainly centered on trying to understand the nature of the near-infrared emission from Sagittarius A, and as an observer, I'm going to try to characterize the behavior of Sagittarius A in the near-infrared timing-wise. So what does Sagittarius A look like in the near-infrared if you, instead of looking at Sagittarius A over many years, instead looking at it in just one night? So this is an example of a night in 2005 where we took images in 3 wavelengths at H, K, and L, so 1.6 microns, 2.2 microns, and 3.8 microns. And you can see that in the middle there's this spot that it sort of blinks on and off, and that's Sagittarius A in the near infrared. You'll notice several interesting things. One is that the Sagittarius star variation happens fairly quickly. This sequence of frames takes place over 3 hours. You can see that Sagittarius star behaves differently than the stars around it. The stars are mainly not variable during the night, whereas Sagittarius star is really variable. And you can also tell the other thing, of course, is Sagittarius star is much redder than the surrounding sources. Okay. I don't really need to go through this given this audience, but this is mainly the what we think about as the quiescent spectral energy distribution. So the near infrared is kind of between where the synchrotron emission is and the synchrotron self-content side of the emission. So it occupies a really interesting area in the SED of the source. And Sagittarius star has been detected right over a very large range in wavelengths, which is really helpful for modeling these effects. So the first detection of Sagittarius star in the near infrared was reported in 2003, and so these are light curves from Ginsler et al. 2003 showing the variability that I was talking about earlier. This is about 2 to 3 hours, these light curves, and then in purple is the Sagittarius star variation, and then in red is what a point source might look like. So this variation, we want to understand what causes this variation, but also to characterize what the timing behavior is. And this is work now done a long time ago, which is to show, I was interested at the time to figure out whether the variations in Sagittarius star can be characterized by a power law behavior in the spectral in the power spectrum. So this is a series of data that we had in the early days. So you can see there's only 6 really well measured light curves at the time. This was I think I was doing this in 2008 or so. And so here you can see Sagittarius star in black, and then in blue is as a comparison source nearby, basically. And you can see already actually some really interesting features here, right? Where when Sagittarius star is it's bright, its amplitude of variation is also large, meaning when it's really bright, it can vary by a lot. And then when it's really faint, the variation is very small. So this suggests a time correlation in the near infrared emission from the source. And the other interesting thing is these variations happen kind of on a scale of several hours. This was already there was already evidence that maybe there's some scale of variation, a time scale for the variation. And so, but first, let's look at the timing characteristics. So if we do something like a Fourier transform, essentially, of the light curve, you get something like this. This is a periodogram. So basically, it shows you the power at different frequencies in time, and the blue is essentially what we observe for Sagittarius star, and then different slopes to the power spectrum are shown in the different colors. So you can see that the Sagittarius star behaves a lot like this alpha equals 1.5 slope, but it's fairly difficult to tell. Oh, sorry, the black is the Sagittarius star. The blue dot is basically the 3 sigma upper limit of the variation. So you can tell it's sort of in between here, close to like 2-ish, but it's really difficult here to measure precisely. This big spike is really interesting. It's not a periodic signal. It's at 3 minutes, and that's the time scale at which we dither the images. So that's why we had to do these simulations in order to match these the observational characteristics. So you can see that this 3-minute peak is reproduced in the simulations. Okay. So that was a while ago, over 10 years ago. What have we learned since then? So now Sagittarius star has been observed with adaptive optics for over 15 years. And so Günther Witzel in 2018 wrote this really nice sort of comprehensive look at all the near-infrared observations of Sagittarius star. So this histogram took a lot of time. It's a combination of 133 nights from VLT and KEK, from starting all the way from 2003 until I think 2006 was when this data stopped. So there's 13,000 points. And so this is just a histogram of the near-infrared flux at 2.2 microns. And then, so you can see that it peaks here, and there's kind of a long tail. So this is a log normal distribution in the flux density. Of course, this work on Sagittarius star has been going on a really long time. So if everyone's interested, these are the many references that have been discussing Sagittarius star infrared variations. The other nice thing is that Spitzer it was shown that Spitzer can observe Sagittarius star. And this is pretty extraordinary, right? Because Spitzer is such a small telescope, but because the Spitzer pointing is very, very accurately determined, one can just basically say, look at this pixel in the Spitzer image, and then just look for the variations in this pixel over time. So you get both Sagittarius star and all the other stars, but since Sagittarius star is the only source that varies, you get the intrinsic variation in the source. So there was a lot of really interesting data analysis techniques to be able to do this, but I won't go over that. I'll just talk about the results, which is that these are now light curves that are up to 24 hours long each, which is extraordinary because you can't get this kind of continuous light curve coverage from the ground. And remember when I was talking about how these variations seem to have a time scale, it becomes like much more obvious when you see these 24-hour variations. You can see like these variations last for maybe a few hours here, a little bit less here, but they seem to have this scale. And so with these data, you can look at this, which is to look at the power spectrum. So what the power spectrum I showed previously goes from about a minute or so up to about a little over an hour. But with these data now, you can go to much longer time scales, so past the hour time scale up to several days. And what you get is maybe I'll show you this first, which is the power spectrum now breaks at this at longer time scales, and this break happens at about 240 minutes or so. And then there's this side, it breaks also, but this is an observational artifact at the moment because this is where the white noise from our observations set in. And this break is really interesting because a lot of times we see in AGN, they also have similar breaks in their power spectrum as well. You can't have in principle, right? You can't have infinite power at long frequency at very low frequencies, but where it breaks off seem to correlate with things like black hole mass. And so Sagittarius star's break happens closer to 4 hours, and that is somewhat in line with the fact that we have a much low mass black holes compared to a lot of AGNs have been studied in the past. And so in 2009, we had some idea that the break should exist. And so this was the contours from the Meyer et al. Paper in 2009. But this new observations with Spitzer and all of the near-infrared data shows we can just basically pin it down really well. And it also shows the slope of the power spectrum to be about 2 as well. Okay. Another really cool thing we've been doing recently is I sort of alluded to this when I was showing the little animation of the center of the galaxy with all the images, which is that now that you know exactly where to look, you can figure out if you can see Sagittarius star much further in the past than 2003. And so this is work done by one of the grad students at UCLA, Joel Chen, and she went meticulously through all of the images and then figured out whether Sagittarius star had been detected. And it turns out that we can detect it actually in a lot of these speckle data. And so here is here's kind of the sequence of all the detections. So the first detections here is in, that was clear, it was in 98. And the other thing that Tuan did here in this case is she removed all the epochs where Sagittarius star could have been confused by a star. So sometimes you can't really tell between Sagittarius star's variation versus when the star just gets really close by. So to eliminate that source of confusion, we just didn't consider those epochs. So the earliest detected free of stars observation of Sagittarius star was in 1998, actually here. Anyway, you can tell from these series of images that they are it's fairly faint, but detectable. And unfortunately, because of the nature of the data taken in these times, we don't have better timing resolution than just the average Sagittarius star flux per night. So unlike with adaptive optics data, when we can take images down to the scale of about a minute in time, you saw that 3-minute spike, for example. These data are all basically many hours combined, basically. But what's interesting is it lets us kind of reconstruct the behavior of Sagittarius star, at least on average, over 20 years. And one of the interesting use of this actually is to think about how Sagittarius star might be changing, right? And there are a lot of reasons to think why Sagittarius star might change. One of which is that there's these gaseous dusty objects, which many of you have heard of, the G objects, have gone through closest approach to Sagittarius star at different times, and so may have deposited gas onto Sagittarius star. So what happened was that there was a source called G1 that went through closest approach, I think around here. And so by, actually, now I forgot when G1 went through, so maybe over here. But what we're trying to do here is to think about whether the passage of these dusty objects can have an effect on the average variations of Sagittarius star. And in this case, the variations don't seem to be different over the time scale here. And so the other interesting thing is that by extending the time scale to the 90s, we can also extend this measurement of the power spectrum further. And it's very basically consistent with the fact that Sagittarius star doesn't vary anymore than it does at 4 hours compared to at 10 years, essentially. So that variation no longer changes. And this is just our expectation for what we should see the distribution of fluxes from Sagittarius star are in this black, and then this orange is what we actually see. So it's pretty consistent. And then just to preview some very soon to be submitted work from Gunther, is that he has now been thinking about a model for Sagittarius star's short timescale variability. So this animation is going to have many plots. So I'm just going to highlight a few of them while you watch this animation. So this is the spectral energy distribution of Sagittarius star. So he's modeling as these two components that are correlated. So they're coupled, so that the variations at the different frequencies, meaning like X-rays or radio and infrared, can be coupled as well. And we've learned a lot about how things are correlated between these different wavelengths. And then in these plots down here, you'll see this is going to be the radio variation. This is going to be the near infrared variations, and this is going to be the X-ray variations. Okay, so I'm going to play this. This is the magnetic field, and then the electron density, I think. Shoot, I've misaligned this. I'm going to try again. Okay, great. So you can see that as these SEDs vary, you get variations in the in what you see in these different wavelengths. And so in the near infrared, you can see that the variation is it's really strong, and then in X-ray less so. And you can see how the X-rays and infrared sometimes correlate and sometimes do not. So this model can reproduce some of the features that we see, for example, that every X-ray flare, we see a brightening in infrared, but not the other way around. Sometimes infrared can be quite bright and you see no X-rays. So I'm not able to do this this model justice, but I suggest talking to Gunther about this model if you're interested in how the very short timescale variability can be explained. Since he's part of the EHC, I'm sure many of you have already know him. Okay, so what's interesting, let's go back to the 2018 paper, what's really interesting is that in the 2018 paper, because we had so much data, and we saw that Sagittarius star was so constant over all these years, we wrote in there, it is surprising how steady the statistical, spectral, and polarimetric parameters describing the variability of Sagittarius star have been since the beginning of AO observations. And so we thought we knew what was going on in the near infrared, even just like observationally, like characterizing it. And then 2019 happened, and then we saw light curves like this. So this is a time-lapse image, a video of Sagittarius star over about 3 hours. And so I don't need to tell you where Sagittarius star is in this image. It's that really bright thing in the middle. So this is the brightest we have ever seen Sagittarius star to be. It got much brighter than even SO2 here, which is normally the brightest star in this whole region. If Sagittarius star had been this bright, it could have been discovered in the near infrared even before adaptive optics, and it would have been easily seen in all the spectral data. And so what does this light curve look like?
This 4 minutes one. Sorry.
Okay, thanks, Jason. I'm almost set. So this is a series of images from that night, and you can see Sagittarius star's variation compared to the stars. And one of the things that's really interesting to notice is that when we started that night, this was the brightest we saw that night. So it was probably even brighter before we caught it. So that makes it even more extraordinary, I think. The other things is that there are really steep drops in the brightness of Sagittarius star in very, very short amounts of time. So just several minutes, it dropped by over half in flux. And so these things probably mean that whatever causing these variations are actually quite small scale near the horizon. And the other interesting thing is it got really, really faint as well. And here I've put both the K-band, which is the 2.2 microns, and then the H-band is 1.6 microns. And I've shifted the H-band data up by about this magnitude 2.45, and they match extremely well. So this suggests that the slope of the spectral energy distribution between 1.6 to 2.2 microns was pretty constant, at least in this bright part of the light curve. So we're doing more analysis now to figure out more carefully how much this change in slope might be as a function of brightness. And what's nice is that because usually this is hard to do because you can't, it's often hard to separate the background stars from Sagittarius star. And so because there's always contribution from some background near Sagittarius star. But this night it's just unambiguous. It's just Sagittarius star shines so much brighter than all the stars that making this measurement is actually a lot less problematic. Okay, but it wasn't actually only that night that was extraordinary in 2019. Actually, several nights, Sagittarius star got brighter than a lot of times. So here's that night where it's really bright. So I've put these dashed lines which show basically the cumulative distribution of all previous Sagittarius star observations for the last 15 years. So above this 100% line means 100% of all Sagittarius star near-infrared measurements are below this line. So it got over twice as bright as the brightest we've ever seen Sagittarius star in the past. And so this is a 99.7%, and this is a 95%. So on this night in April, it got above the 99.7% of all previous nights. I've made all the scales the same way as this night, so it looks less impressive, but these are really impressive flares, actually. This is, it goes out to 95%. And so you can basically compare the distribution. So in gray was that same histogram that I showed from Günther's 2018 paper. And then in black is the histogram from normalized to 2019. And you can see this long tail of really bright emission. So we think that statistically speaking, at least, 2019 behaved quite differently than what we had seen before. And there are two kinds of hypotheses we've been thinking about. One is that maybe there something was interrupted or changed about the accretion flow onto Sagittarius star, because that's generally what we think is causing these variations ultimately onto Sagittarius star, is how much material comes in, is how in the end gets reprocessed and how bright we see it. So one idea is that SO2 went through closest approach in 2018 at about 100 AU from Sagittarius star, and so that could have gravitationally affected the accretion flow, perhaps. The other idea is that there were these objects called G1 and G2 that passed by Sagittarius star in the past. So, for example, G2 passed by Sagittarius star in 2014, and this source, there's a lot of debate over exactly what it is, but we know that at least on the outer parts of it, it was highly affected by Sagittarius star, meaning Sagittarius star could have stripped some gas from this object, and it just takes time for gas to fall into the center. And I'll just preview a little bit of work from Elena Mirchakova, who recently did this calculation of how long would it take gas to fall from wherever the pericenter of these objects are into Sagittarius star. Does it match up with 2019, basically? So this x-axis is basically 2019 minus the infall time, when it was she thinks that the length of time it takes for the gas to get in, and then this is the pericenter distance of these objects. So SO2 is down here. So it turns out SO2, if SO2 disrupted the gas, we shouldn't have seen it in 2019 yet. It should take actually a couple more years. And there are various measurements of the G1, G2 orbits. So some orbits of G1 would say that it's not consistent with what we see, and some orbits would say it's more consistent. That's the same thing for G2 as well. And so I think Elena has put this paper up on arXiv, and so I think it should be available on Monday, actually, for those interested. So anyway, in conclusion, I don't have a good explanation for what was going on in Sagittarius in 2019. We were really excited about 2020 to help answer this question. For example, is 2020 seeing these activities? And due to COVID, we have not enough data to answer that question, sadly. So in the end, we end up these questions. What is the time evolution of Sagittarius star's behavior? What would a new statistical model of Sagittarius star look like? Is this a precursor to a larger event? And how do we narrow down the physical mechanisms causing this activity? So thank you very much. I'm happy to take questions.
Questions, welcome to speak up, type them in the chat, raise hands, any function available to you.
Maybe I can start.
Yes, please, Monica.
With question. Yeah. So, Tuan, I was wondering about this bright event in the Sagittarius in the summer of 2019. Have you tried to look at the or investigate or characterize the fluctuation on the top of this, light curve? Is it similar to what we see? In the previous slides at the beginning, you showed these different light curves, historical, flares, and we see some substructure in them, right?
Yeah.
I think there were even claims that you see some, periodicity maybe. So do you see something similar? Have you investigated the character of fluctuations on the top of this?
Yeah, that's a good question. We are trying. It's with only a few nights a day, it's just very hard to statistically get a really good sense of it. But qualitatively, I would say like the variations seem fairly similar, though it is really interesting that for long periods, the variation is very small, like in terms of substructure, right? And if you look at it things look a little bit different in magnitudes versus fluxes, obviously because of the scale factors. But you see it falls down quite generally smoothly in this case, rather than where is it at the beginning? I think this is what you mean, right? Which is like these variations seem to be yeah. So it's a really interesting question, but I think one that it's hard to definitively say at the moment.
Okay, I think.
Yeah, thank you for your comment. Thank you.
I think Stefan was gonna ask a question or comment. More 2019.
Yeah, hi, Tuan. Congratulations to all of you.
You too.
So I think I just want to add that also the gravity data in 2019 actually show that Sagittarius A appears to be a bit brighter on average in these flares than they did in the 2 years before, where we also have gravity data. So I think that's observationally the finding is fully in line. We didn't have such an exceptional 60 millijansky flare as this one here, but statistically, it's in the Gravity 2019 paper on the flux distribution. You can see that the 2019 distribution does not match the older distributions.
Yeah, that's a really good point, Stefan. Yeah, I forgot to bring up, but right, there are various other evidences that is that a word? There's various other evidence that Sagittarius A was really bright in 2019, including this gravity data. I think there were some X-ray results from Swift as well that showed that maybe there were more flaring activity in X-rays.
Okay, Shidant, sorry if I butchered that. Please go ahead.
Yeah, hi. Thanks for the talk. So can you go to your second last slide where you talk about where you show the infall time? Yeah. So is there like a time scale for how much time it takes for gas not only to fall in but also to heat up and emit radiation, or is it just the time it takes to fall in? Because if the time is comparable, for the gas to also heat up and brighten up, so you can add in more sources there.
So I would assume that the time scale for heating up is much faster once the gas gets there. But this is work from Elena, and I think she's in the audience. So Elena, do you want to?
I basically agree with Tuan. I think the assumption is it takes years to infall. For G1, for example, it depends which particular estimate for the orbital parameters you use. It like between 10 and 20 years. It's more than enough to heat up.
Elena,
but I'm happy to talk to you, like if you want in person.
Sure. Thank you.
And Lena, since you're already unmuted and speaking, do you want to ask your question? And then...
Yes, I had a question. Tuan, do you have any observations since COVID?
No, sadly. So we got a little bit of data in with imaging this year, but not enough to really say one way or another, sadly. Yeah.
Thank you.
Okay. And then probably this should be the last question, unless there's one more question after this. So Jacob, please go ahead.
Okay. So thank you for a great talk. Just wondering, maybe you already answered, but is there any X-ray observation of the 2019 big flare?
Are they? Oh, so not simultaneously with this really bright one, but there was a multi-telescope campaign that was happened in 2019. So that included X-ray, Spitfire, and gravity as well. And I'm not sure if the paper on that has come out yet. So the Chandra observations, as far as I know, don't seem to show that many extraordinary flares. So the X-rays I was talking about is with Swift. So Swift is a satellite that looks at the Galactic Center basically once every 24 hours. But it is much less sensitive than Chandra. And so typically they only get like one flare a year from Sagittarius A. But I think in 2019 they got 3 or 4 or something like that. And so the rate of occurrence seemed to be much higher than they expected, and the timing of it was also very similar to the sort of May to like July-ish timeline.
Yeah, you don't need to put anybody on the spot, but is there an X-ray observer in the audience who might want to comment on anything? Is there any? I'd just be very curious. Is there any outstanding X-ray behavior in 2019? Gabriella, Sarah, I know you're there. I don't know if you want to comment on it.
I was waiting to see if any of the direct observers were here, but as far as I know, there's nothing really statistically as interesting as what they're seeing in the infrared.
We can also return to it in the discussion at the end. Oh, I see Gabriella.
Oh, here's Gabriele. So.
Yeah, I tend to share the same point of view as Sarah.
Okay. Great. Okay, well, we should move on. So let's thank Tuan again. Silent clapping. All right. Thanks a lot for the great talk.